Hello everyone! So the USACO US Open contest just ended, so in this video I'm going to be showing you how I did the first problem from the gold division of that contest. During the actual contest I only solved one problem, but I only wanted to solve one problem, so I achieved my goals and therefore I am satisfied. Alright. So, the problem statement. There are n cows in a line, and every cow has a breed. A delegation consists of an interval of cows. Cows at the end of the delegation are called leaders, and they cannot be the same breed as any other cow in the delegation, including the other leader. So the question is, how many delegations are there? So I've included my code in a GitHub repository. There's a link to it in the description below. You can see it's pretty short, so it's most important to understand the reasoning behind it, because if you just read the code, you probably won't understand why it's that way. So this video is intended to help you out on that front. I'll give you a technical interview so that you all can first know what's going on and then figure out the why later. As always, during these videos, if you ever get confused or need to take a moment, just feel free to pause the video and think through it a bit more. First, we're going to need a Fenwick tree. If you don't know what that is, I'll include a link in the description for more resources. Initialize an array to keep the last occurrence of each breed. Initialize the answer to 0. Then we loop through all the cows and do some complicated stuff. We loop through the last occurrences of each breed and calculate unique breeds within the range last occurrence to end, and then we add that to the total, and that's pretty much the overview. So I'm going to explain all of these steps in detail. I just want you to know the overview so that you know the general picture as we go through the explanation. So now let's go to an overview of what the video is going to be like. First, we're going to show that we can essentially reduce this down to counting the number of unique breeds within an interval. Then we can count the number of unique breeds within an interval, and then we apply that algorithm to the problem. So first up is reduction. We want to show that the core of this problem is finding out how many unique breeds are within an interval. So here's an example. We have a row of cows, 1, 2, 3, 4, 5, 6, 5, 4, 2, 2. Those are the breeds of the cows. For example, let's let 4 be our leader. We want to ask how many delegations exist with this cow as the leftmost cow. The delegation, first, must not contain a cow of breed 4, because obviously one leader is 4, and the conditions state that we can't have any other cow be the same breed as the leaders. If the right leader is of breed 5, then it must be the leftmost 5, because if it was the rightmost 5, then there would be a 5 in the middle, and we can't have leaders being the same breed as any other cow in the delegation. In other words, every unique breed in the range contributes to one delegation. One more thing after we count that is the last occurrences of breeds, because if a leftmost leader is the last occurrence of its own breed, then it can be a leftmost leader for all the remaining cows in the row, but still only one delegation per unique breed. This is also the case for breeds that only appear once, for example, this 6, and now we get into the unique range query bit of the problem, finding the number of unique breeds within an interval. So first up, we're going to have to use Fenwick or binary indexed trees. I'm going to leave a resource in the description just in case you don't know what these are or need to review them, but I'll just give a quick overview right now. So Fenwick trees have an implicit array, so this is not explicitly declared, it's an idea of sorts. So for example, this could be our implicit array. Fenwick trees are a way to calculate prefix sums of this implicit array in O log n time, so it makes it very fast to calculate prefix sums. So for example, querying at this location will give 3 because we want to find the prefix sum of this much. So Fenwick trees have two operations, update and query. Update updates a element in the implicit array by however much you want, and query tells you the prefix sum of any prefix. Alright, now let's get on to unique range queries. So we have this example. We want to find the number of unique breeds in the blue interval so that we know how many right leaders there can be. Using our Fenwick tree, we'll take the range sum query of our implicit array in that range. And our implicit array has a very specific meaning. It denotes representative cows for their breed. For example, in this example, we have the representative cow being the rightmost 5. So taking the range sum query of this only gives us 1 5. Of course, the representative cow might not be the cow that can actually be a right leader, but remember, we only want the number of unique breeds in the range, so we don't need to know which cow can be a right leader. So keep this idea of representative cows in mind because it will be very useful for our problem. So now the actual algorithm. How do we actually use unique range queries to solve the problem? First, we sort queries by right endpoint. This is very important to keep in mind. Then we initialize the array to keep track of the most recent occurrence of each breed. These first two steps are rather simple, so we'll be going into the third one. We iterate through the cows and perform 3 specific operations. So we'll be looking at the third step in detail. So we have this example. We have our cows and we have our implicit array. We've looped through the cows, and now we're on this index, which points to a cow with breed 4. We also have our implicit array. So the first 2 steps. Change the previous occurrence's value in the implicit array to 0 if it exists, and change the current index in the implicit array to 1. So that would modify our implicit array to look like this. Essentially what we're doing here is updating the representative. So remember that notion of the representative cow that represents its breed within a region so that we only count it once. Basically, we're updating it from the previous occurrence to the current occurrence. And why do we want to do this? Well, we want to do this so that future queries count our current cow. Because otherwise, if it was, for example, in the middle of the last occurrence in the current cow, it wouldn't count the current cow. So we want to update the representative so that it's the most recent. And we can do this because if a future query contains the previous cow, it must also contain the current cow. And that is because we sorted the queries by right endpoint. And we'll look at 3 possibilities of why we can do this third step. So first possibility is in the future we have a query that has its right endpoint somewhere to the right. And we go all the way to the back before both of our current occurrence of the breed and the previous occurrence. In this case, we still only count the breed once, and we only want to count it once. If it's somewhere in the middle, it counts our current breed once. Remember, if the representative stayed behind, then we wouldn't be counting this breed at all. So that's why we need to update it. And if it's somewhere in the future, we don't want to count the breed at all because it doesn't exist in the query interval. After those first 2 steps of updating the representative, we do the third step in the loop, which is if a query has its right endpoint here, then we can compute its value. We don't actually want to include the index itself in the range because we don't want to include the current cow's breed in the number of unique breeds between the current cow's and the previous occurrence of its breed. So in this case, we can just take a prefix sum using our Fenwick tree, and that gives us 2 unique values. This is basically counting the number of representatives within that range, and each representative corresponds to 1 unique breed. Now we've talked a lot about queries. What actually are our queries within the context of this problem? We've talked about this before, but let's just restate it. We want the unique range queries for ranges between consecutive occurrences of a breed. For example, here, this is the range between consecutive occurrences of the breed 4. Therefore, we do a query every time our current index's breed has a previous occurrence. And this happens to line up nicely with our algorithm, as we'll see. We also want to do queries for ranges between the last occurrence of a breed and the end, and we want to do it for breeds that only occur once, because it's very similar to the last occurrence of a breed. Now that I've described the algorithm in detail, let's go over the whole thing once more. First, initialize the Fenwick tree, initialize the last occurrence array, and initialize the answer to 0. Then we loop through the cows. If the current breed has a previous occurrence, then we can update the value of the previous occurrence's index in the Fenwick tree implicit array to 0 because we want to shift over to the representative. And we calculate unique breeds within the range using the Fenwick tree by taking prefix sum of the implicit array to get the number of representatives. We want to do this because if the current breed has a previous occurrence is one of the conditions for the queries that we want. We're kind of doing this out of order in the way we described and in the code, but that is absolutely fine. It doesn't make any difference. Next, we update the current value of the current index within the Fenwick tree to 1. This is moving the representative over. And then obviously we have to update the last occurrence array to keep it up to date. After looping through all the cows, we want to make sure to include all the delegations that have a left leader that is the last occurrence of their breed or that only occur once. So we loop through the last occurrences of each breed and we calculate the unique breeds within the range index of last occurrence and end because that last occurrence can be a left leader and it doesn't have any rightwards restrictions. And that's the summary. I encourage you to go back and rewatch the parts that may have been confusing or less easy to understand or less intuitive. And that's it for the problem. Again, code is in the description. Hopefully that made sense. If you have any feedback or any questions, feel free to drop a comment down below. So thanks for watching, and I will see you next time.